Welcome to these lectures on algebraic geometry and commutative algebra. In the last lecture I have stated three formulations of Hilbert's rule standards and we wanted to prove their equivalence. And let us recall quickly what we have proved so far. So, what we proved is the following. So, as usual our notation is L over K field extension, and we have defined the maps VL and IK. These are the maps. This is a maps from ideals of radical ideals of the ring R to the K affine algebraic sets, K algebraic sets. This is a subset of the power set of L power n, and then we have defined a map from power set of L power n to radical ideals in R, and R is our polynomial ring in n variables over the field base field capital K. And this actually we have defined for actually from any ideal, but it depends only on the radical of that ideal. And what is HNS1? HNS1 says if L is algebraically closed and I is an ideal in Gothi K, this is ideal in R and A is not R, then V L of this ideal is non-empty. So, that is at least one point in this algebraic set. HNS2, that is if I take any ideal again L algebraically closed, A is any ideal in R, then if I take IK of VL of the ideal A, then you get back not A but the radical of it. So, in particular if A were a radical ideal, then you get back your ideal A. So, and HNS3, this is completely algebraic formulation, has nothing to do with these maps. So, if I have a field extension capital, let me write field extension of this base field K. So, that is E over K field extension, and E is K algebra of finite type, then E over K is algebraic. That means every element of E is algebraic over K. Actually, we will prove that actually E over K is a finite extension. In particular algebraic. So, finite extensions are algebraic. And what did we prove so far? So far we have proved that HNS1 if and only if HNS2, and also we have proved HNS1 implies HNS3. These we have proved already. So, I will just mark this is proved, this is proved, and now we want to prove, therefore, what remains to prove is this implication, this remains to prove, which we will do it today, and proof of HNS3 proof. These two things are remaining. So, if we prove these two things, which we will do it today, then we would have proved that all these HNS 1, 2, 3 are equivalent and they are all true. So, now let us prove HNS 3 implies HNS 1. So, proof of HNS 3 implies HNS 1. So, what is to be proved? So, we need to prove that we have given L is algebraically closed. Also, we have given an ideal A in the ring R, which is a polynomial ring over K in n variables, and A is not the whole ring R, it is a non-unit ideal. Then to prove that VL of A is non-empty, that is, we want to find a point A equal to A1 to An in L power n such that f of A is 0 for all polynomials f in the ideal A. This is what we need to prove. And what is given is HNS3. That means whenever you have an whenever you have a finite type K algebra E, which is a field, then it should be algebraic extension. That is what we have given, that is HNS3. Alright, so what do? We have given an ideal A which is not the whole ring. So, by Krull's theorem, we know that there exists a maximal ideal M in the ring R with A is contained in the maximal ideal M. This is Krull's theorem, because given any non-unit ideal we can always enlarge to the maximal ideal. And now we choose that maximal ideal and put E equal to R by M. R by M is polynomial ring in n variables over K modulo the ideal M. So, it is clearly that this E is a field and it is extension of the field K, and also and E is K algebra, E is a K algebra of finite type. That is because this is a residue class algebra of the polynomial ring, and that is precisely what we mean by the algebra of finite type. So, since E equal to K x1 to xn modulo M. So, it is a finite type K algebra, it is a field, therefore, we can use HNS3. So, by HNS3 E over K is an algebraic extension Now I want to use one fact from the field theory. So now since L is algebraically closed, L is algebraic closed field extension of K. So therefore L is a K algebra. So it's I want to draw the diagram. So that is E to K to L, there is a injective, this is extension of the fields, and there is an extension E here which is a field of K, and we know this extension is algebraic. Let me write it little bigger. This extension is algebraic, and also know this is algebraically closed field. Then one of the result in basic field theory says that we can extend this inclusion to E. So that means there exists a K algebra homomorphism. So I will write here, there exists a K algebra homomorphism. Let me call it phi from E to L, which extends the inclusion. This is fairly easy theorem in field theory, so I will leave it for you to check this. So I will only mark here this check. So once we have that, then that means what? And remember, so I will draw again the diagram on the next page. So we have E here, which is residue class of the polynomial ring by the maximal ideal M. This is K and this is algebraic, and this is L, and then we have extended this phi. This we have extended it to L. This we called it phi. So therefore phi of this, so let me also denote the elements here, K small x1 to small xn. The small xi's are precisely the images of capital Xi mod M residue class. So this phi of Xi makes n small xi, and those are elements in L. So I will call them AIs, and then therefore I have A equal to A1 to AN. This is in L power n, and then my natural choice is to check that this element belongs to V L of A. So to check that A belongs to V L of the ideal A. Alright, but what is the ideal A and M relation? So A is contained in M. So therefore VL is inclusion reversing, so VA is contained in VL of M. So it's enough to check this, it is enough to prove that it is even in VLM. So enough to check that A belongs to VL of M. What does that mean? That means, so that is f of A is 0 for all f in M. But well, this phi is a map from these to L. So what is f of A? That is precisely so if you take any f in M, then this goes to 0 under this homomorphism. So phi of, so this follows from so f belongs to M, that is f bar, which is f which is the image of f in E, but this image has to be 0 because f belongs to M. Therefore, modulo that it is 0. So, therefore, this is 0. So, phi of, because phi is a K algebra homomorphism, phi of f bar is also 0. But what is phi of f bar? This phi maps this excise that we have called it AI. So, therefore, this is nothing but phi of f of small x1 to small xn, but this is 0. That implies f of a1 to an is 0. So, that proves this. So, that proves A is in VL of M, but then it proves in VL. So this proves HNS 1. So, with this now we are only left to prove with HNS 3, and of course one can prove any one of them, either HNS 1 or HNS 2 or HNS 3, and then therefore they will be all true because we have proved their equivalence, and I will choose to prove HNS 3 because it is the simplest to prove. Well, one can also prove HNS 1. HNS 1 is the next simpler to prove, and HNS 3 is the strongest result. So, it will be more difficult to prove, but this equivalence shows that we do not have to prove that. Alright. So, now we will prepare to prove HNS 3. So, once again, what do you need to prove? We need to prove HNS 3. So, what we need to prove is, if I have a E over K field extension, and E is a finite type K algebra, which is a field, then we want to prove that E over K is an algebraic extension. This is what we need to prove. Well, and to prove this, I will state two lemmas, and then we will use these lemmas to prove this HNS 3, and that will complete the proof. So lemma 1. Actually, I will state lemma 1 and prove it, state lemma 2 and prove it, and then come to the proof of HNS3. So what is lemma 1? Lemma 1 is, so suppose that A is contained in R, contained in B extensions of rings, rings always been commutative and with identity elements, with a Noetherian ring and B is an A algebra of finite type and B is a finite R module. You should remember the difference between finite type algebra and finite R module. Finite R module means it is, as an R module, it is finitely generated, not finite as a set. And algebra finite type means it is, as an algebra it is finitely generated. Okay, under these assumptions, then R is an A algebra of finite type. In particular, R is Noetherian. R is a Noetherian ring. Because A is Noetherian we have given, and this R is, conclusion is this R is a algebra of finite type, therefore by one of the corollary to Hilbert basis theorem, this in particular part is clear. So in particular part I will just mention here by HBT, Hilbert basis theorem. Alright, so proof. So let us write down first what are all given in the notation. Alright, so what is given? A is Noetherian, that is given, and then we have given that this B is a finite type R algebra, finite type A algebra. So we have given that this B is A x1 to xr. It's as an algebra is a finite type, means this is generated by, as an algebra by these R elements, and this square bracket means as an algebra it is generated by that, or this means that this is the residue class algebra of a polynomial ring over A in R variables modulo some ideal. Okay, that is this given, and then we have also given this B the finite R module. So we have also given that this B, the same B, so I will write equality here, this one is as a modulo over R, it is generated by finitely many elements. So this is modulo over R, these are linear combinations of finitely many elements, y1 to ys, small ys to small y into small s. Now what am I going to do is, I am going to put yi equal to x r plus I for I from 1 to s. And why do I do that? If B is generated by this y1 to ys, then I can put more element there, also still it will generate the whole B. Similarly here, so then this will also be equal to A and I will also put m equal to r plus s. Then this A I could write, I added more elements. So still it will generate because this generating set is contained there. And similarly, this will be R x1 to xm. Because I have added x1 to xr here and I have added xr plus 1 to xm here. So what is the achievement? Achievement is they as an algebra over A, B has the same generating set, and as a module over R, it has the same generating set. That is a good achievement. You will see the neatness in the proof because of this. Alright, so now these xi and xj, if I multiply xi and xj in the ring B, this is in the ring B because both were elements in the ring B. On the other hand, so this is a R linear combinations of the x. So this is equal to summation A I j k xk. This sum is running over k from 1 to m, where these aijk's, they are elements in the ring R. Fine, because as a modulo over R, it is generated by these x1 to xm. Alright, now I am going to concentrate on these coefficients and consider A prime sub algebra of R. This is a sub algebra of R, A sub algebra of R generated by these guys. There are finitely many of them. So I adjoin with A. So A adjoin with A I j k, where I j k are varying from 1 to m. So this contains A. This is a sub algebra, A sub algebra of R generated by these finitely many elements. So obviously this is a finitely generated algebra over R. So obviously A prime is Noetherian by Hilbert basis theorem, because it is finite type algebra over a Noetherian ring. Alright. So now, and what is that we wanted to prove? We wanted to prove that R is a finite type algebra over A. That is our aim. So I will write the goal. So goal is what? R is an A algebra of finite type. That is the goal. Alright. So first I claim, claim as an algebra, as a modulo over A prime B. So B is also modulo over A prime. We have given A, B is a modulo over R is finitely generated, and it is generated by this x1 to xm. But now I want to claim that this B is a finite A prime module with the same generating set. So claim is B is A prime combination, A prime linear combination of x1 to xm. We know that B is generated as a R module by x1 to xm, but this says that B is generated as a prime module by x1 to xm. Alright, so why is that? So for this, what are the elements of B? Elements of B, we know B is generated as an algebra over A by x1 to xm. That means every element in B is a sum of monomials in the small x's. So it is enough to prove that every monomial in small x, that is x power alpha, this means this is calculus notation, x1 power alpha 1, xm power alpha m, this already belongs to RHS for every alpha equal to alpha 1 to alpha m in n power m. Because every element of B, we know that every element of B is a polynomial in the small exercise. I am not saying unique, but it is a polynomial expression in the small exercise. That means it is a finite sum of such monomials with coefficients in A, that we know. So if I prove that all these guys are in RHS, then whole B is in RHS because A is also contained in A prime. And how am I going to prove this? This we will prove it by induction on the, this is proved by induction on mod alpha. Mod alpha is sum of alpha 1 to alpha m. Okay, so the assertion is very clear for, so clear for mod alpha equal to 0. That means all these indices are 0. That means this x power alpha is 1, and therefore it is clearly in A, and therefore it is, assertion is clear. Assume that mod alpha is bigger equal to 1, and we may assume and alpha 1 has to be bigger than 1. If alpha 1 is 0, then you interchange with some other alpha, interchange exercise, therefore we can assume alpha 1 is bigger than 1. And then what is x power alpha? X power alpha will be, x1 will come out times z, and now z is a monomial in x, small x, and the degree has dropped by at least by alpha 1, which is positive, so at least by 1. So therefore this z is again combination of A prime linear combination of this x1 to xm. Therefore this, which is equal to x1 times summation I from 1 to m ai prime xi which belongs to, so where, so I should write where ai prime, they are in A prime. So this is because we have written z equal to summation I equal to 1 to m ai prime xi. So we have assumed this by induction hypothesis. So therefore I plugged it in that z here and we got this, and now we push that thing inside. So this is equal to summation I is from 1 to m ai prime x1 xi, this, but x1 xi I know again that is in linear combinations of this xk with this coefficient, they are now in ai prime. So this is clearly belongs to RHS, this clearly belong to summation I is from 1 to m a prime xi, which is RHS. So that implies claim, this claim that B is generated by this. Once you have proved the claim, then what did we prove? That, so we have proved, so this proved that it's a finitely generated modulo over A prime, and A prime is Noetherian by Hilbert basis theorem. So this proves that this proves that P is a Noetherian A prime module, and therefore every submodule is finitely generated, and R is a prime submodule of B. So that implies R is a finitely generated A prime module. But this A prime, this is finitely generated A prime module, and this is finitely generated A algebra. Therefore, altogether R will be finitely generated A algebra. So that will prove that AR is an A algebra of finite type. That is what we wanted to prove. So this proves lemma 1 completely, and then I will take a short break, and after the break we will complete the proof of HNS3. Thank you very much.